I think a suitable quote to start on is in order. Space is big, really big. You just won't believe how vastly, hugely, mind-bogglingly big it is. The Voyager 1 spacecraft from beyond Pluto at the edge of our solar system looked back at us and took a photograph. That's MODOT, that is us, and at 3.7 billion miles from Earth. Alpha Centauri, our nearest star, is 4.37 light years away from Earth, about 1 followed by 13 zero miles. Voyager has gone a fraction of a percent, about 0.00001% of the distance. Light has a finite speed. An interesting consequence of this is that what we see is not how space currently is, rather is how it used to be. For example, when we look at Alpha Centauri, we see it as it was 4.37 years ago. When we look at the Andromeda Galaxy, we see it as it was 2.7 million years ago. When we look at Centaurus A, we see it how it was 13.7 million years ago. We see them in the past simply because light takes time to travel from them to us. A nice way of thinking about this is in the concept of a light cone. Think of yourself at the vertex in the middle of the cone. Now time goes forward along the vertical axis, splitting into your future above and past below. Distances from you are along the horizontal axis. In the future, the edges of the cone represent how far light can travel in the given time. That is, the further ahead in time, the further the light could have travelled. As nothing has been found that can travel faster than the speed of light, this represents the furthest away anything can travel. Now for the past, the bottom part of the cone. The inside of the cone represents everything that could have reached you, given your current position in space. That is, the further away the object that's emitting light is, the longer the light has to travel in order to reach us. And so when we see it in the past. How it was, not how it is. In 1929, Hubble found that the redshift from stars, that is the change in the wavelength of light from those stars, grew with the distances of the stars. Moreover, he found the velocity of the object away from us is proportional to the distance of the object. The further away, the faster it moves away. This was the first piece of empirical evidence for the Big Bang theory, that the universe was expanding. You may be familiar with the concept of the Doppler effect. In your day-to-day lives, when a car is driving towards you, it sounds distinctly different than when it's driving away. This is the Doppler effect. The same effect affects light, just as it affects sound. And so the change in wavelength that Hubble observed from stars corresponds to them moving away from us. Shown now is Hubble's original plot. Obviously, his results seem very approximate given the scattering, but this was 90 years ago, so it has been improved. For a comparison, see the current graph. The small box in the corner? That's Hubble's original results.